pretty much of that diagram is covered with those shaded areas, so we know quite well, we know a lot about these collisions. What we investigated is the size of typically a micrometer down to up to some centimeters at velocities between 10 to minus 4 meters a second up to 100 meters a second, and we did that basically with silicates and recently started with some ices, and no experiments to my knowledge have been done with oxides or organics, or even in higher size ranges. It's simply not feasible in laboratories. Everybody can imagine that. And what we see is this diagram, which is the same as this actually. This, what appears here to be blue, is the observed mass gain. So in these collisions, particles stick together, they grow. What is this dark orange? Is mass loss, and in between there's this yellow area. So we have mass loss, meaning fragmentation or erosion, and we have mass gain or mass conservation. And I will show you all these experiments linked to those letters, the letters linked to a recent review paper where this links to the chapters.
When you distinguish between, mass loss is mass loss from one.
Yeah, it's, for example, if a large body, I will show you in the experiments, if a large body collides with some smaller and the larger bodies, or if there are a lot of smaller bodies afterwards, then it's not growing. The larger body did not grow, so it's mass loss because there are several small ones afterwards.
Is it the average mass of a particle resulting from that collision, or is it the mass of the largest particle after the collision?
No, it's not the average mass. It's not the mass of the fragments, it's the mass of the largest fragment. Okay, basically, if we talk about mass loss. I will show you in more detail. These are all the regimes I will talk about, the experiments and the models. So we have 5 types of experiments, which roughly, from left to right, have increasing velocity. So we have sticking without compaction, we have rebounding with compaction, we have sticking and compaction, rebounding and fragmentation, and rebounding, sticking, and fragmentation. And these are the related experimental works. And we have 2 models, a microscopic model, molecular dynamics code, and a macroscopic SPH model. And I will also tell you about that and tell you about the tests of those models and parameters and things like that. So, I will use 2 slides for each of those experiments. The red one is the one I'm treating at that moment. So the first one is sticking and no compaction. And first of all, I'd like to focus on the so-called ballistic cluster-cluster aggregation, where we assume that we have a gas where all the dust particles are monomers, and then we have this collisional cascade where 2 dust particles collide, they stick as they hit each other, and in the next time step those dimers collide and we have quadromers, and the quadromers collide and we have octamers, and after a certain time we get some fractal aggregates. And we see that after a certain time step, the size of these fractal aggregates is all the same. So we speak about monodispersity in that case, and this is what we observe in these experiments. This is a space shuttle experiment from 1998, where we observed these fractal growth of 1.9 micrometer sized spherical SiO2 particles, and another experiment from 2000, which is a sounding rocket experiment, also microgravity experiment, and these grew to also these large chains, which are fractal. And the second part is the ballistic particle cluster aggregation. So we have a larger cluster, and single particles are aggregating. So it's growing by accumulating single particles, which is not easy to do in the lab, as one can imagine. So we do something quite similar, which is called the method of random ballistic deposition, where we use individual particles and deposit those on a substrate. In our case, we use a special filter. We deagglomerate a powder of SiO2 particles. They couple to a gas flow. This gas flow is led through the filter, and the particles are deposited on this filter. And what comes out is something like that. This is a macroscopic aggregate, 2.5 centimeters in diameter. You see that height is approximately 1.8 centimeters or so. And this is highly porous. This is what we call a dust cake. So whenever I mention the word dust cake, this one is what we call the dust cake. And this macroscopic aggregate of 1.5 micrometer SiO2 spheres, which you can see here. This is an SEM image of that dust cake, so you see the spheres. And this is very porous. It has a porosity of 85%, so 15% volume filling factor. So there's a lot of void space in there. And one can also model this. If you model random ballistic deposition, this is what comes out. And this also, for those particles, has a volume filling factor of 15%. So this is in very good agreement with models. This is the first phase. So the velocity is, the particles are small, micrometer sized, and the velocity is below a meter a second.
Is the difference in shape between the experiment and the simulation due to the way in which you deposit the particles, or?
You mean the curvature of the surface?
Yeah.
Yes, it is. It's because it's led through a tube. Because we have, this is done at roughly 1 to 3 millibars. And then we have this gas flow, so we have a vacuum apparatus, and it's led through a standard vacuum glass tube, and that's why we have these boundary effects. This one is a very high one, so if they are typically they are in the height of 5 millimeters or so, and then they are quite flat on the surface. This one is, it's a very high one. So the second type of experiment is what you see here, or in the sketch. 2 aggregates. This time we cut out these aggregates by means of a razor blade from our dust cakes, the larger dust aggregates. So these are 5 millimeters, 3 to 5 millimeters in size. And they collide in a microgravity environment. So we went to parabolic flight aircraft, built our experiment inside the aircraft, performed these collisions at 40 centimeters per second relative velocity at in this microgravity environment, and what we see is the particles are rebounding at these velocities. At little lower velocities, Bloom and Münch did some similar experiments in 1993 at 15 centimeters a second relative velocity, 50 and 1 meter a second with different particles. So this again is SiO2. Here there's zirconium silicate, and what we observe in these experiments, as well in these experiments, we have a coefficient of restitution which indicates compaction. The coefficient of restitution, for those who are not familiar with the dynamics of collisions or with bursts in series or so, the coefficient of restitution is the ratio of relative velocity after a collision and relative velocity before a collision. So you divide the collision or the particle's velocity after the collision by the velocity before, and you get a coefficient which is usually named epsilon. So this is what you see here. And if you square this, it's a measure for the energy which is conserved in the collision. You have a question?
Yeah, I was just wondering, judging from this video here, I mean, it must be very geometry affected, right?
Because these are tubes.
Well, yeah, at least just for me, looking at the video, you have slope surfaces,
sure.
impact. So, what kind of errors do you have in this?
Oh, this is not from this experiment. This is done with almost spherical particles. This is done with those cut-out particles. And here also the filling factor is a little bit higher. So these are, they have a porosity of 74%. Of course, we have some errors. These errors are very small, as far as I remember. and these errors are, they are quite large, especially in that axis, because this is the squared normalized impact parameter, meaning 0 for a central head-on collision and 1 for a grazing collision where only the top surface layer touches.
So even for sphere-sphere collisions, as a function of angle deviating from central collisions, all of the parameters will change, including this one. The contact time, the energy.
Yeah, sure.
Contact
Here you can see basically the impact angle on that axis. So for a central collision, this is what you see here, and this is squared, so this is the energy, and you can see here that roughly 2 or 3% of the energy is conserved. And this is what we also see here. It's less than 5% of the energy is conserved.
It just strikes me as adding even more difficulty having an irregular shaped impact object as well, as in this video.
Yeah, it's
But you are using spheres. So,
yes.
How can you have something beyond 1 if there's spheres on this video overall?
Yeah, that's not easy to explain. There's some artifacts due to measurement, of course. Particles can if they are not perfectly spheres, then you can go to that values, and you can also go to epsilon higher than 1 when you have some rotation before the collision and no rotation after the collision. You have some transformation from rotational motion to translational motion, so you gain some kinetic energy in the translational motion. So this is only the translational coefficient of restitution. And now one has to ask, where is the energy? So what happens? We took a dust aggregate, again a cube, put it on a shaker, which had an amplitude of 100 micrometers and a frequency of 100 hertz, and we shook it all the time. And what we see is, at the beginning, it's a cube, then the corners are eroded, so they are definitely lost, they break off the aggregate, so we lose mass in that place. And afterwards, the mass stays constant, we measured that, and the aggregate is getting smaller and smaller. So it's getting more compact, so the filling factor increases. And this is what we see here. We see the volume filling factor, which is initially at 15%. So this is an artifact due to this cubic shape. And it's initially at 15%, and then it increases to roughly 33 or so after 2,000 or 1,500 collisions. So it's getting more and more compact, not in one individual collision, but in several collisions. There's an effect we can see. And this is what happens in these bouncing and compaction regime of, this is I think 20 centimeters a second. So the next regime is sticking and compaction. Here we see, again, several millimeter sized aggregates impacting into a larger dust cake. You see again the curvature of the surface. So we have they're coming from here, so we have a steep angle over here and a shallow angle over here. Velocity is 90 centimeters per second. And this one is even more porous than the spherical SiO2 dust cakes I mentioned before. This has a volume filling factor of only 7%, because it's made from irregular shaped particles. So we have bigger particles, we have smaller in between, so the porosity increases. And what we see here is we have sticking due to geometrical effects. If the video starts again, that would be great. You see that those particles bury themselves into this dust aggregate. They cannot be released from that aggregate again, because they are buried that deep that due to geometrical effects they have no way out. They would have to go out the way back they came in, and that's absolutely unphysical. And the impact at the shallow angles, there sometimes we see that the particles can get out due to geometrical reasons.
What's the cohesion of it impact us? Is that less? Well, that is larger than that of the target.
It's the same material.
The same material.
It's absolutely the same material. So the impactors are taken from one of those. And what we see here, this is a little bit confusing on the top. I will show you this one on the bottom for clarification. So we see a regime of bouncing, and we see a regime of sticking. And this is taken from experiments where we dropped a sphere and not an aggregate into this dust cake. So same experiments as I showed you before on the video, but this time with a glass sphere of same mass, so a little bit smaller than these ones. And we see that the shallow collisions, so high squared impact parameter, rebound, and the very fast bury themselves wherever they hit, because they penetrate very deeply. So high velocity leads to growth in this case, sticking, and very central collisions may lead to growth. This is the sticking due to geometrical effects.
It's all this vacuum, right?
This is all in vacuum, yes. By the way, these were also microgravity experiments, so there's no effect of gravity. So the next regime, where we go to velocities of 5 meters per second over here, and what's this? I think it's 2, 3, 5 meters a second. We see that the particles are breaking apart. We have some larger leftover fragments and a lot of small fragments in that collision. This is in the lab, no microgravity, but the gravity, of course, as it is known, can be calculated and subtracted from the data. So what we see at low velocities, 2 meters a second, only some small fragments are broken apart, and only some bonds are broken. At even higher velocities, or at higher velocities of 3 meters a second, some more fragments result, and at high velocities of 5 meters per second, there's a complete destructive disruption of that body. Again, this is spherical SiO2, which was recently measured at our lab for this experiment. And see that to have a look at the impact parameter over here, because it looks very central, but maybe it is not. We introduced a 3D optic into that system, so we see the same particle from 2 different viewing geometries, and this is the collision we already saw, I think. So we see a lot of fragments moving all over. This is recorded with a high-speed camera of like 5,000 frames a second, I think. And the result of that is we have a mass distribution of fragments. This is again from Bloom and Münch 1993, which is also included here. We see that for different velocities, the normalized mass fraction follows a power law with a constant slope. So with higher velocities, from here to here, the slope just shifts. It doesn't change. It's not getting steeper, so it's just shifted to the upper left corner. So there must be some general fragmentation law with the same slope. It's plus 3.5 or so. And what we see here, mu is the mass of the largest 2 fragments in units of the initial mass of the impactors, plotted over the normalized impact energy. And what we see is it follows for central collisions. The green ones are from Bloom and Münch 1993 for central collisions, and it follows kind of curve like this. We do not yet know how to interpret it, but we see that it follows a curve for a central collision, d squared equals 0, and of course for a perfectly grazing collision there's no change. They are not disrupted. So this is the region where the fragments can be. And the last regime of experiments, this is bouncing, sticking, and fragmentation. We take a dust projectile, this time filling factor of 35%. We use an accelerator, a gas accelerator for that, collide it with a solid glass wall, And what we see is the fragments are distributed in a very shallow angle of roughly 20 degrees. And we see this bulge over here, we see some left over, so there's some part of that particle sticking to the this SiO2 target. And again, we see the slope is independent of the velocity, the slope of the fragment. So we tracked every fragment from here to wherever it goes, like 300 fragments or 500 fragments per collision, and know pretty much the velocity of each fragment and the size of each fragment. And so here on the bottom, you see the fragment distribution for 1.2 meter per second impact velocity, and on top of that 8.4 meters. So we see for different impact velocities, the slope doesn't change, the function is only shifted to the top left corner, and here we discover this due to the resolution of the camera.
Just to understand, is this the velocity belonging to both parts of two particles, for example, or for each part, or is it only from one part and the other is more stable?
Usually, if we take the velocity, we mean the relative velocity. Meaning, if two particles collide, we take the velocity in the center of mass system. So, but in this case, this of course is fixed to the experiment setup. So it's the velocity of this one, and it's against gravity, so gravity points downwards. And this is of course calculated out of this later on. Then there are some more high velocity impacts done at the group in Münster by Gerhard Wurm and his colleagues. And what they see impact, they have the accretion efficiency, meaning there's no accretion if there's 0, and there's accretion in percent. You can see on that axis. And as the impact velocity increases, the accretion efficiency also increases, so to roughly 50%. At velocities above, let's say, 13, 14 meters per second. So they accelerate their dust particles, similar dust particles, which are a little bit more compact with 34% porosity. They accelerate those with a crossbow, which you can buy in any weapon store. They build that into a large vacuum chamber and fill their dust sample into that and shoot it to a dust target. And what they also see is the fragment size follows a power law, but at a certain limit of roughly 0.3 millimeters or so, the fragments do not play a role anymore. And what I already showed you, the very shallow angle of the fragments is also seen here with even higher velocities than I showed you before. So these fragments leave the target in an angle of, let's say, 3 degrees to both directions.
So these are basically the same qualitative type of experiment as you just showed before.
Yeah, there are some changes. So this is the velocity into a solid SiO2 dust target. So it's not to a glass plate, but it's a dust target. And what they did is they put a strip of sticky tape around that dust target and saw in which angle the fragments hit the sticky tape. They were caught by the sticky tape, and so they know the angle is roughly 3 degrees.
In your previous picture, you were showing the cumulative mass fraction.
Yeah.
That means accumulated over smaller masses, right?
Accumulated over smaller masses. This is simply.
I mean, you start with smaller masses and it grows. Or what do you mean by cumulative mass fraction?
It's the sum of all fragments smaller than.
Yes, right.
But
you have this cutoff error, this error in the determination. As you.
This is the detection threshold.
Does this not affect the estimate of the cumulative mass fraction, or?
No.
Oh,
This
so
is not. This
yeah.
kink is not real. It's because we simply cannot see the size of the fragments, because then the resolution of the camera is not high enough.
Yes.
We see 1 pixel, even though it's only a half pixel or quarter of a pixel or so on that side. Yes?
I have a question. I mean, when you start with this, all rests on, I mean, you first get this two little glass balls together in the stick.
Yes.
So there's a sticking coefficient for that.
Yeah, unity.
Yeah, right. But in reality, the sticking coefficient varies. So all these slopes and these kinks and this position and all that might very much depend on the sticking coefficient.
Yes, but
that tells you, for instance, the fragments. I mean, this tells you how tight these things hold together when they bounce onto something.
But at the very beginning, when you take two micrometer-sized spheres and you bring them into contact, they stick.
And there is
With the sticking coefficient of unity.
There is not a chance that there is a collision efficiency, for example, when you stick.
They stick. That's the so-called hit and stick mechanism.
But imagine you're in a dust cloud out there in the universe somewhere.
So what is the dust
Some
material?
little particles, like, let's say little ice particles, we have others like silicates, and the ice particles, when they get together, they have, of course, different sticking than maybe some silicon particles or something. And then these things hit each other, and you don't know how this accretion starts. Maybe it starts first with, let's say, small ice particles, they get bigger.
Yeah, but there's a regime without the ice particles, close to the protostar, inside the snow line.
This is inside the snow.
Oh yes, it's not. This is dust aggregates, so silicates. Of course, outside the snow line there's ice. There are different types of ice, different materials, but nobody has done any measurements about that, as far as I know. Unfortunately.
But I think forgetting the fact that you are inside, I think the general point is that if you had two different types of dielectrics, then it might not be the case that 2 micron sized particles that are different dielectrics may not have a sticking coefficient of unity.
Maybe. Okay, so we leave the experiments, we go to the models. First of all, the molecular dynamic microscopic model. I'm not a theoretical physicist. I did not develop those models, so I just briefly tell you what those who develop those models can do with those and what they need from our experimental group. First of all, there are microscopic parameters involved, the rolling energy and the breaking energy. This is measured by Heim et al. They measured the pull-off force of a sphere. They glued it to a cantilever of an atomic force microscope and pulled it off and measured the pull-off force. And then there is the breaking energy measured by Poppe, who shot those silicate spheres onto each other and saw a sticking probability of roughly unity, and above a certain critical velocity of 1 meter a second, it dropped almost to 0. And then the rolling energy was measured by Heim et al., as well as this one with this atomic force microscope. They built a chain of particles and they bent this chain and measured the force. And what you see here is this chain formation, and of course here's some electrostatic effects. They have some charging and sticks to the cantilever. But they pretty well measured those parameters. And the model says, so these two, sliding and twisting, are not important, so it's all described by stretching or the breaking, and the rolling by a quarter of the circumference of these monomers. What you see here is a 2D simulation with that code at different velocities. I will address that later. Let's first have a look at 5 phases of collisions described by Dominic and Thielens, who modeled that. So first, if the impact energy is less than 5 times the rolling energy, we have sticking without restructuring. If the impact energy is roughly 5 times rolling energy, we have some first visible restructuring. And if the impact energy is roughly the number of bonds times the rolling energy, we have the maximum compression without losing any monomers. If we achieve like 3 times the number of bonds times the breakage energy, we lose a monomer. And if the impact energy is bigger than 10 times the number of contacts times the breakage energy, we have a catastrophic disruption. This is what they define as their state. And so here they modeled this for different velocities for 0.1 micrometer sized 2D spheres. So this is not representative, but in the meantime they already did computations with 3D aggregates at 50 centimeters per second, and they stick. And at 2 meters per second, and they fragment. Not catastrophic, but well, they fragment. So a first test for that model is whether we can, we have to find out whether we can apply these models, whether it's true. So Bloom and Wurm measured in 2000 the phases 2, 3, 4, and 5, and compared that to the model by Dominic and Thielens, and it fits pretty well. So what you see here is some images of that experiment. You see sticking, and it's still fractal. You see compaction, which is phase 3. Phase 4 is not shown here because a single monomer, I don't know how they recorded that. And this is a catastrophic disruption when they collided with something. So you see these parameters fit fairly nice. That's the first test. The second test is the static compression. So what was done is a dust aggregate was placed in between or glued on a flat surface, and there was another surface brought on top of that, and it was in one dimension. It was pressed in one dimension with a certain pressure, and at each individual pressure the area and height was measured, so we knew the volume and could determine the volume filling factor, which follows this law, or this curve. So the shaded curve is the experiment result, and all these dots are numerical simulation results of Paschen and Dominic, which also kind of fits. Third test is the measurement or determination of the sound speed in that media, which was done by Paschen and Dominic. You can see here all these dots are simulation results, and this small shaded area in the center is a measurement from our group. So also a third test fits. The second model is the macroscopic model, the SPH, smooth particle hydrodynamics model, where numerical particles are treated and the input parameters are macroscopic material properties, the compressive strength, the shear strength, and the tensile strength. Again, the compressive strength can be derived from this 1D curve I already showed you, the Bloom and Schrebler curve, or in the meantime we already did that in 3D, which is then this one, which yields roughly the random closed packing. The tensile strength was also measured by Bloom and colleagues in 2006, which fairly agrees with roughly 1,000 pascals, which is very low if you compare it to the compression to the tensile strength of solid materials of 10 gigapascals or so. It was done in a very similar experiment like this, but this time the plates were removed from each other, not pressed together.
Is the tensile strength, does that wind up being a sensitive function of the packing fraction?
Yes, should be. It should be depending on the number of contacts.
Yeah.
Sure. So it's decreasing with increasing porosity. So then some results from Valverde et al. They measured compressive strength and tensile strength for printer toner particles, and these results were taken by Sirono, and he modeled these collisions. Here you can see a plot of the density in a collision. I cannot judge how good these model results are, but this is the first approach of SPH methods where they took these results from Valverde et al. And there's recently also another SPH code from Schäfer et al. But what they see is they have here two examples with almost similar or with similar parameters. So the outcome is significant different. So here we have growth of spherical body which consists of two half spheres, which is not likely, and with very similar parameters we have complete disruption of the body. So this has to be tuned. There are some tests for these models, and here there are some results from Arakawa et al. Experimental results, and the model by Sirono. And Sirono claims that his model fits the experimental data. So what he sees is, or what we see here is the ejector angle in an impact of very high velocity, and we see a slope, or we see an increase of ejector angle, and that's what also Sirono modeled. We don't know whether he's thinking of this increase or not, and he's giving all the numbers in terms of the Mach number for porous ice, which is also not known as far as I know. So I cannot judge how reliable these models are. He at least claims that those models are. And another thing is, here you can see the velocity of the fastest ejector in numbers of the impact velocity as a function of porosity. So here is a high density, here is a low density, so the very porous media, no, here's the low density, the very porous media, the ejecta are very slow, and for solid material the ejecta are very fast. Sirono gives a similar plot, but he doesn't plot the porosity, but the shear strength, which is, as you heard before, related to the porosity, as you asked before. So the trend is the same, but it's only quantitative, I would say. Back to the model by Schäfer, not to the Sirono model. Here are experiments from Carsten Güttler from our group. He dropped an impactor into a dust cake, a dust surface, and measured the intrusion, the penetration curve. So time resolved, he measured the penetration and can plot a deceleration curve like that. So we have depth over time, and we see there's high velocity impacts due to deep penetration and long penetration time, and the slow ones are decelerated very fast. And if you normalize those to the point of first contact and the point of deepest penetration, you get a master curve like that. So all the experiments are plotted here, and this dashed curve is the SPH model of Schäfer, which the guys in Tübingen computed for us. And there is some agreement. It's not perfect already, but well, this is part of a recent DFG project, so they have just started with that. And what we see is it follows kind of Hooke's law without relaxation, which is also kind of strange. We have not yet explained that.
Is there any analysis after the fact of the relative compression of the impactor and the substrate?
The impactor was a solid glass sphere, and the compression is what you can see here. This is the solid sphere. We X-rayed the sample, so it's 3D X-ray tomography, and we see an enhanced compaction or enhanced density in the area here. What we see here, this is the volume filling factor. In terms of the sphere volume, in terms of the sphere volume, so the main volume is compressed from 15% to roughly 23%, which is roughly here. And this is also what the model gives as a result. And the model shows this strange slope which you do not see here. But what you cannot see very good is here is a sphere, and here is this strange slope. And one must admit that this is, of course, 3D, because it's an experiment, and this is only 2D, and very recent data from last week or the week before. And then we have a fourth test, which is the fragmentation of a body which impacts. I already showed you that. And there's also a model which is not yet calibrated, but it shows the same features. So I'm done with my time, or?
Yes. Oh, yes.
That's bad. I haven't even told anything about the Saturnian rings, but, well, okay. So, just to conclude the models, the microscopic model needs the rolling energy, the braking energy, and the macroscopic model needs compressive, shear, and tensile strengths. This handles real particles, this handles numerical pseudo-particles. The limitations of the molecular dynamics code are 1 million particles. Here we, of course, can handle bigger bodies due to the fact that the numerical particles are representing more than one individual particle. And the calibrations can be done. I showed you where the calibrations were done from Valverde and from Bloom and Schrebler and Bloom et al. Experiments, and from those atomic force experiments and impact experiments of Popper and time. And I showed you all the tests. And the predictive power of the molecular dynamics code is not yet known to our minds. And of course, the SDH code can investigate larger particles as soon as it's calibrated. But for that, or for the test, we need to know whether C, S, and T exist for porous media or for dust aggregates or so on. And yeah, well, I'd like to close here.
Thank you very much. Talk is open for discussion now, please.
Does this have anything to do with Saturnian rings?
No, the Saturnian ring part is that one which comes here. Well, we talk too much about the other things.
Okay.
I could show you some more slides about Saturnian rings.
How about
If you give me some time.
If there are other questions, then those could go first.
Sure.
Yeah, one question. So, are you saying that the thing that you showed last, the impact onto a bigger body, that this is the most efficient way of aggregation, or what is compared to equally sized bodies?
At least this leads to growth.
Yes.
Which is, yeah, we need growth to grow to kilometer size.
And then
there are some other effects which are not included in that. We have some recent experiments on collisional charging, which then could lead to accretion of small charged grains and so on. But there are no experimental results which I could show you now, because this has just started.
And can you say anything about the growth time it would take to go from there's a certain amount of density, surface density, if you apply it to the protosolar nebula, how long would it take to go from micro-sized to centimeter-sized particles?
I'm not sure about that timescale.
But I mean, what would it take? What would it take you to actually come up with such predictions?
I think there
Could it be
are
done
such
already?
predictions.
What?
I think there are such predictions already.
And are they such that it would work?
I don't know.
Less intensive.
I think Wiedenschilling and Kuzi.
Wiedenschilling and Kuzi, yeah.
Is,
I think they calculate something. I can look it up, but I don't know it by heart. Sorry.
I mean, in this MD model, there's definitely just contact potentials, let's say. But how big I didn't get how they found the parameters on the role and
they were measured in experiments. They simply took the experimental results. They needed that for the experiments.
And that's all they needed, essentially.
As far as I know, yes.
So I was just wondering, with all of these different parameter regimes, you can do a calculation for how much of the energy has been transmitted to sort of bouncing off particles, or you can ask how much of the energy has gone towards compacting the initial particles. If you do those sorts of balances, you must be able to calculate how much goes into heat. I suppose is going to be the ultimate sort of difference between what you started with and what you wind up. And does the fraction of the energy transmitted to heat change? Is that sort of a constant through all these different regimes, or does that change a lot?
I don't know how much is going to heat. We fairly know how much is going to compaction, or that a lot of that is going to compaction.
So I mean, like, is heat sort of like a small player, or is that like a large player in these regimes?
I would guess it's a small player in this regime.
Because it radiates efficiently, one would think.
Yeah, it's a huge surface.
If it does. Does it?
But I mean, there's a lot of friction to change the packing fraction by this amount. So the heat is probably certainly crucial in the energetics, but when the collision is over, the heat is dissipated quickly.
Yeah.
If there are no further questions, maybe we can see a bit about the Saturn rings.
Yeah.
It's only 3 or 4 slides.
Yeah.
So I guess I briefly tell you what we do and what regime we're probing. So this is a radio quotation image of Saturn and its rings, and everything which is blue, which is not very well represented by this projector's colors. So everything which is blue is represents particles below 1 centimeter size, and then we have green particles between 1 and 5 centimeters, and purple particles bigger than 5 centimeters, and the white one is too dense to give any assumption of the particle sizes. So this is the size regime of the main rings, the dense rings, and Zepka gives a size distribution. So the most particles are centimeter size. So that's what we want to investigate, and that's what we started to investigate at the beginning of the year with an experiment to find out some critical parameters for the rings, what people who model the rings, who model ring dynamics, need, because they stick to very old data. So they cannot explain the thickness of the rings, which is below 5 meters. And so they are very thin. 5 meters, that's not a lot for such a huge system. So they need to know how energy is dissipated, all these disturbing effects from moons and gravitational interaction from nearby bodies. And what we did is we built this experiment, we rebuilt an experiment and collided ice particles. These are some millimeters at 40 centimeters per second. And also, so here you see the ice particles. This is not very elaborated right now, because these are simply, I think, what people like to call the hyperquenched amorphous ice or so. So we dropped, with a syringe, we dropped water into liquid nitrogen and took out the balls. And here we have bigger particles of 15 millimeter size, which were frozen in a mold inside a kitchen freezer.
And what temperature is the experiment?
This experiment is done at 130 Kelvin, and this one is done at 110, with bigger particles with some frost on the surface, but arbitrary frost. So we left it for some minutes at the air humidity. So these are the experiments for the Saturnian rings. For ice collisions, we did, and we want to elaborate on that by doing multi-body experiments. This is done with glass now. We have a glass test chamber, and we inject the particles with a certain velocity in the Bremen drop tower facility in microgravity, and watch what happens if this granular gas cools dissipatively. So we need to go to velocities which are realistic for Saturnian rings, which is below 5 millimeters a second or so. And what we managed is the gas cooled down. Here's time, here's the gas velocity, and we see that at least after injection of the particles, it follows Huff's law, which is the velocity goes with 1 over t, or energy goes with 1 over t squared. And we see that we can go down to a couple of millimeters, and or some individual collisions even less than a millimeter. And what we see is what has to be investigated more is we have spinning of particles, we have strong rotation, transition from translational motion to rotation, and this is what we recently started. So we know that epsilon, the coefficient of restitution, is 0.64, so we can dissipate energy quite effectively, and this is what we're aiming at for ice particles in future experiments. I think that's all I can like to tell you about circular rings. For first to ask your questions about that, please.
Okay, so the particles were all forced to be in the same plane, or almost in the same plane. Was there a certain
Those particles?
Yeah.
Yes, it is a glass box,
Yeah.
and the particles are 1 centimeter in diameter, and the height of the experiment chamber is 1.5 particle diameter. And we tried that to do even more 3D with 1.9 particle diameter. But then the problem is that particles are overlapping quite strong, and that numerical or a computational analysis of these collisions, which are a lot, like 100,000 or so, this is not easy then, because the overlap here, the overlap is moderate, but if they can overlap very much.
That was also in microgravity, yeah?
That was in microgravity, yeah. That's a 9-second microgravity period in the German drop tower in Bremen.
You could probably do it using lattice-Boltzmann methods. If you, simulation could proceed fairly well using lattice-Boltzmann methods, I think. So similar experiments were done not in microgravity to look at a granular Rayleigh-Taylor instability by Adik Flakoy in the University of Oslo. So it's the same sort of experiment.
Yeah, there are a lot of those experiments in the granular media community done, and they know pretty much about dissipative cooling gases, granular gases, and we'd like to do it with ice in the future, so we will build a huge cooling block, thermal reservoir around the experiment, and try to make similar experiments with icy particles. And that's what then goes into simulations of the group of Frank Spahn in Potsdam University, when they model the stability and development and evolution and lifetime of the Saturnian rings.
Okay.
Yes.
So there are some people who work down the hall from me in Boulder who don't actually believe that you can create large planetesimals by having, just mutual collisions building up small objects into larger objects, and they can't figure out how that works, and so they've given up, and they've decided that larger planetesimals may just form from gravitational instability in the disk.
Yeah, I know those theories.
Those characters. So, are the experiments that you're doing, would they shed light on the types of collisions that you would have in a sort of gravitational instability event, or? I actually don't know the answer.
I don't know as well. I wouldn't dare giving some estimate now.
Estimate the velocity with which the thing, collapses and
I'm not that familiar with the gravitational instability in detail, but
I'm not either.
I know that some people needed to create planets in a fast way.
Yeah. There have been some interesting numerical studies done recently where people are showing that you can create these waves in the nebula, and you get turbulence, and so.
Are you referring to Anders Johansson, or are you referring to Anders Johansson's work, or?
No, I'm trying to think who it is. It'll probably come to me over coffee. Yeah, anyway, there's some new numerical stuff on that, so it would be interesting to estimate those velocities and see if it's similar.
So, at the moment, this doesn't aim at any relation to gravitational instability. What we might look for is some pattern formation, because that is expected in dense granular systems.
Yeah, there's been some stuff on like pattern formation for the regime appropriate for Saturn's rings, but I don't know whether the size scale of the particles is comparable to what you're doing. I suspect it's like much bigger particles. So.
Well, I showed you the size distribution of the rings, so it's the majority of the particles, the number